Let's talk about another topic called electron affinity. I think this is the third and last topic that I want you to worry about, that is going to be using lots of trends in this chapter. The only remaining topic that is not included in this chapter that talks about trends is electronegativity, which we are going to talk about in chapter 5, but in the given lab, I did include electronegativity because it comes with the electronegativity as a part of the workup. So electron affinity is defined as the amount of energy released or absorbed when an electron is added to an atom in its gaseous state. So we haven't quite discussed that part yet, but from next chapter, chapter 5, we discuss these elements as either part of ionic compound or part of covalent compound. Whenever we say word ionic compound, which means there are going to be ions. An ion is an element that forms different charges by either losing electron or gaining electron. So far in the ionization energy, we kind of talk about how easy or hard it is to lose an electron by discussing about ionization energies. Here we are discussing about electron affinity values, kind of leads to a topic of how easy it is going to form a negatively charged ion for each element in a periodic table. So electron affinity is again going to talk about the amount of negative energy released when an atom in the gas phase accepts an electron. So released means talk about inherently, is the element is going to be more stable or less stable after it accepts the electron by turning into negatively charged anion. Here, these are the values. Let's find if there is any trend. Again, obviously there is going to be a trend. Here it is showing that from left to right, electron affinity values are increasing. Okay, from top to bottom, electron affinity values are decreasing. Okay, let's see. What it meant is if an electron is added to chlorine neutral, if I need to show you in terms of energy levels, a chlorine that is neutral in gaseous state on the energy level, it is here. And if we let it react with an electron, right, if we force that chlorine to react with an electron, it will react with it and it will accept it, but then it loses about 349 kilojoules per mole by forming into chlorine anion. What does it mean to us is, in terms of energy levels, anything that is at lower in energy in chemistry is more stable. Come on. More stable, less stable. So a plus value means actually a good thing. So if it is releasing lots of energy, which means it is more happier by accepting that electron. If there is going to be a negative value, which means it is not that crazy to accept that electron, which you can see it in these noble gases. Noble gases are completely filled electron orbital shells, and if we convince them to take one more electrons, they are going to say no, 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 which means they were going to need to input energy for them to be accept the electrons, which means by accepting electron, they are going into unstable mode by accepting that energy and electron. That's why you can see them in the negative values. If you see a positive value here, it is a good thing, because whatever that positive value is showing that big amount of energy is lost by the that single neutral element by forming into this anion. So here you can say that using these electron affinity values, you can predict which one of the elements are more affable. Affinity means, affable, likelihood to, like that particle. Which one of these more elements are going to like to have one more electron, which one of these elements do not like to have one more electron, by discussing this electron affinity topic. Let's see. Here the trends again from left to right, electron affinity values are increasing. Okay, and from top to bottom, electron affinity values are decreasing. So it is more easier to predict the trends from left to right than right to left, from top to bottom. But still, we are going to discuss an example how to discuss the trends from top to bottom, why it is not likely to take an extra electron. So here you can see that you can find the trends again for different groups. That is for period 1. And from sodium, I need a different color. From sodium to chlorine, again, because we are excluding noble gases because they do not like to take in any more electrons because they were noble gases. This is for row 2 and some more elements until 3, 4. At least you can see that from left to right, for example, here, left to right, lithium to fluorine, electron affinity is increasing, which means the farther down an element is in the periodic table, farther the right side, it is more likely to accept the extra electron. One of the reason is that if it accepts the electron, it's going to receive the noble gas electronic configuration. That's why elements on the right of the periodic table in general have greater electron affinity values, is just by accepting that extra electron, even though it is hard to accept an extra electron that belongs to that particular element because there is going to be electron, new electron repulsions. Still they accept it because at the end they are going to gain the electronic configuration of noble gases. That's why all of these elements on the right side of the periodic table in a row from left to right, they are going to have much larger electron affinity values because by the end of the day they were more stable by accepting the extra electron. So here are a couple trends to discuss. Here it is saying that if you have two different groups, okay, in general, it is a little bit easier to add that extra electron to an orbital with a much lower energy subshell than a much higher energy subshell. In general, we know that in each shell, NS is in lower in energy than NP, then ND, then NF. So in general, it is easier to add electron here than here. So once it is easier to add electron in a particular element, it's going to lose a lot of energy. That is how we read it. I know it's a little bit complicated by this time already because we just talked about Z effective, then ionic radius, then ionization energy. If you need to take a break, I totally understand, but you need to watch it because we need to know about electron affinity. So another trend is, again, if you're trying to add an electron to an element, again, electronic configuration matters. If you have electronic configuration, again, we're talking about same group. If you're talking about electronic configuration, in general, if you have an empty orbital, it is much more easier to add an extra electron than trying to pair an extra electron to already partially filled orbital. So this is going to, the first example here is going to have much easier time to add an extra electron than this example. Okay. which what it means in terms of electron affinity values is this is what most challenging. We can predict in which case it is going to be much more easier to add an extra electron. But what makes students confused is, okay, in the first case, it is easier to add an extra electron. What it means is if it is easier to add extra electron to a neutral element, once it receives that extra electron, it's going to lose lots of energy. And we predict the stability of we predict the electron affinity in terms of how much of energy it is going to be lost from an element. So if it is going to be easier to add an electron for an empty partial orbital, so it is going to have much more favorable electron affinity values than adding an electron to a already partially filled orbital, which means instead of an element losing energy after it is adding the electron, it actually need us to input energy to add that extra electron. Okay, so just like the ionization energy values, why it is, how it is easier to remove first electron and harder to remove second electron. Similarly, electron affinity values also have a trend. It is much more easier to add one electron than two or more electrons to an element, because adding an extra electron means you are increasing the electron-electron repulsions between electrons of that particular nucleus. That particular nucleus. If you're adding one more extra electron than the first electron, you're increasing those attractions, repulsions between electrons and electrons to a much higher level. So that's why it is not going to like to more in general, they are not going to like to add an extra electron. Here you can see this classic example that in the first case, by adding the extra electron, it released energy. How do you know? Is from this sign. There is no negative sign, which means there is a positive sign, which means energy is released out. Whereas in the second case, energy is shown in a negative charge, which means you need to input energy here and force this negatively charged oxygen ion to accept the second electron, converting to oxygen -2, which means it is not a favorable step. Means we need to force the oxygen negatively charged one to take the extra electron. But in the first case, we don't have to force it much because it is releasing energy, which means by accepting the first electron, it is actually being more stable. So it is doing that voluntarily. But in the second electron acceptance, it is having problem because it is going to be found at much higher energy. So if I have to write in energy diagram, if you have oxygen here, by accepting electron, it's going to lose energy by forming oxygen negative charge. The difference is plus 141, becomes more stable. But if it accepts, if this one accepts one more electron, it will need about 741 kilojoules of moles of energy to input. We need to force it by giving that energy to it. So in terms of stability, this is more stable compared to that, and this is neutral oxygen is partially stable, and we call this one as unstable because it is not easier to add that extra electron. If not, it is a little bit, wrong to say it is unstable. In other than saying unstable, it is harder to convert into negatively charged 2. I'm not saying that it is unstable. It is harder to convert them to negatively charged 2. In comparison to another elements, oxygen 2 is still stable, but it is more harder to convert into oxygen negatively charged 2 by giving 2 electrons to it. Okay, let's discuss a couple examples here. For each pair of elements, indicate which one would you expect to have the greater first electron affinity value. Okay, so to have the first higher electron affinity values, so you need to know the trends again. So it's saying electron affinity values are increasing from left to right, right? But also electron affinity is a little bit challenging because you also need to worry about electronic configurations as well. So let's find where alumina is and the silicon is in the periodic table. Here you have alumina and silicon. So we are asked to compare between alumina, silicon, and phosphorus. And we are asked to say that if you need to add one more electron to each one of these, which one is going to be having greater electron affinity values, which means which one is going to accept more happily, so that it releases more energy. So in general, across the periodic table, in general, we say that as you go right to the element in a periodic table, you will have a more electron affinity values because they were getting closer to the noble gases on the right side of the periodic table. So I would say silicon should have a greater electron affinity value than alumina, because it is to the right of the alumina, and it will have a greater Z effective charge, in other words, compared to alumina. That's what we learned, right? Z effective charge increases from left to right across the period. If you have greater Z effective charge, it is going to attract the electrons much more efficiently. So if it has greater Z effective charge, if you add one more electron, it's not going to have much trouble accepting that electron compared to alumina that has less Z effective charge. So silicon should be having greater electron affinity values. I see the reason why phosphorus is included here for us to compare. If you go back to that electron affinity values comparison table here, showing the values, it's all right. I'm showing the values so that you can see all the elements in group 5 are a little bit different than rest of the elements. It is an exception. That's why it is included in that case. Group 5A do not follow the trend. The reason is because it's electronic configuration values. The electronic configuration of silicon ends with 3p2, 3s2, 3p2 for silicon. Whereas electronic configuration of phosphorus ends with 3s2, 3p3. So just like any other group 5A elements, it ends with partially filled p orbital, partially completely filled p orbital. So what we learned in the previous couple of slides is if you're trying to add an electron to an element, it is easier to add an electron. Two cases we discussed. It is easier to add an electron to smaller subshell than the largest subshell, but that case do not apply here. We are adding both the electrons to just a p subshell. And if you're going to add to the same subshell, you need to check if you're going to add that electron to completely empty orbital or partially filled orbital. 3p2 means you are adding an electron here. Let me write here. 3p2, you're adding electron here. So new electron is going to join here for silicon, compared to phosphorus, electron here, electron here, electron here. So new electron is going to add here because it is 3p3 for phosphorus. So this one is easier to add, this one is not that easy to add. So silicon should have a greater electron affinity value than phosphorus. Again, it is just one group that is an exception. Otherwise, rest of the elements in the period across left to right follow the same trend. So silicon greater than alumina, an exception is this, silicon greater than phosphorus, even though it is to the right of the silicon. Okay. Basically, it's what's showing here. The valence electrons diagram for alumina, silicon, and phosphorus. Why phosphorus is an exception? Because it has already completely partially filled electron configuration, which makes it harder to accept the second electron through painting. All right. After this topic, we are going to talk about a little bit less rigorous topics in this chapter. So far, we had very rigorous topics that sometimes can be challenging to some students. So far, as a summary, we talked about uh, other than introduction to the periodic table and its history of the periodic trends, we focused a lot on Z effective and its relationship with the atomic radius, and ionization energy and electron affinity. I want you to be really good in these three topics: the relationship between Z effective with its ionization energy and electron affinity, because I'm going to test you a lot on these three topics. Okay.